Hello, it's Peter here with the physics of golf on the moon. We're solving a projectile motion question. A professional golfer on the moon hits a golf ball from the tee at a velocity of 75 meters per second at 10 degrees, so 10 degrees to the horizontal, and from a tee, so the ball's right down near the ground in the beginning. And we're asked to calculate range, maximum height and the flight time. So when you're solving a projectile motion question, think about what this is going to look like. So it's going to be the full parabola. It's going to we're going to assume landing at the same level as it began. So here's the golfer just here, and that's the flight or the trajectory of the golf ball. First thing to do when you do these kind of questions is to decide which way is positive. Is up positive or is downwards positive? And it doesn't make any difference which way you pick. You get the same answer. The point is that you stick with whatever you choose. Be clear to yourself. That's the direction I'm saying is positive. The second thing you need to do is to take that initial velocity vector and turn it into components. So 75 at 10 degrees, and we're going to get the horizontal component and the vertical component, and here's 10 degrees, so horizontally 75 by the cos of 10, that comes to 73.9, and over here 75 by the sine of 10, and it gives 13.0, and that's also meters per second. So that was step 2. Step 1, get your direction of positive. Step 2, we've got the components of the velocity. And now we're going to, in this case, I'm going to now think about what's happening in the vertical direction. Remember, the key to solving this is to treat the horizontal motion separate from the vertical motion. So I'm choosing to start with vertical, so I can actually tell myself vertical only. So I'm really clear. I'm restricting myself to thinking it's going to go straight up and straight down. What would happen? So I'm going to choose these 5 variables, and this is about kinematics. So here's the 5, it's all the variables, and that's the only ones I'm going to have to deal with. If you need to, as a reminder, there's those 5 variables, there's what the quantity is, and there's the units. So in this question, displacement, well, that's what we'd like to know. We'd like to know the maximum height, so how high does it go, as long as I'm only talking about half of the flight. So I'm going to make myself a note again. First half only, meaning the first half of the flight, so up to the top. So I'm kind of restricting myself down to that as well. In that case, this is the thing that I'm going to find. That's what I'm looking for, or one of them. Initially, vertically, 13, and it's in the positive direction. The final velocity as you go up, and then you come to the top and you stop, well, 0, final velocity, first half only. Acceleration, well, usually we just put down negative 9.8 because it's in the negative direction, 9.8, and that's the Earth. So the moon, divide that by 6, 1.63 meters per second squared, 1/6 of the gravity on the moon. And how long does it take to get to the top? We'd like to know that too. We know 3 things out of the 5. That means we can find the other 2. Which one will I go for first? got to look for the time first. So if I'm looking for time, then which equation, I'll cover that one up, which equation has got these four in it? Yep, it's V equals U plus AT. 0, substituting in now, 13, it's going to be plus a negative 1.63 times what I'm looking for. So time, I'll put this over the other side, I'm going to get negative 13 divided by negative 1.63, which is the strength of gravity, and I'm going to get, well, I'm going to get a bunch of decimals. I'm going to call that 8.0 seconds as the time to get to the top of the flight. So that's one thing. Now, how far is it to the top? I've got 4 out of the 5 now, so any equation that's got displacement in it is going to be useful to us. And I'm going to choose this one. Substituting in 0, 13 squared to negative 1.63, and S is what we're looking for. So I'll end up with, if I crunch the maths on that one, I'll end up with the displacement being negative 13 squared, 169, over negative 3.26, which 51.84, which is about 52 meters. It's a fair way up in the air, 52 meters when it's at the top. Now I'm going to switch over to thinking horizontally, horizontal only, and I'm not going to do first half this time. Now I'm going to go full flight. So flight time will be double 8. So 8 seconds to the top, 8 seconds coming down, 8 times 2, 16 seconds for the full flight. This time there's no acceleration, so you can ignore acceleration for horizontal motion because we assume uniform velocity horizontally, and initial and final will be the same figure. So I've just got 3 variables to worry about this time, S, V and T. S is the thing I'm looking for. Initial velocity, well, that was the horizontal component, 73.9, and the time we just figured out there, 16 seconds. And now I can work out displacement horizontally, which is what the range is. Range is how far it goes horizontally. Now the one I always remember is V equals S over T. It's kind of what the definition of velocity is. But we want S, so S equals Vt, just putting the T over with the V, and we get $1,182, and I'm going to round this up as well and call it 1200 meters. Don't want to be too fussy about it. That's only 1% error anyway between here and here, so it's pretty close. So there's the range. That's a long way. That's 1.2 kilometers. Imagine being able to hit a golf ball and it goes 1.2 kilometres. Wow. And it's just because the gravity is a sixth of what it is on the Earth. So there's the range. We'll ask for flight time. There it is. And the maximum height, there it is. So there's our three answers. So that is solving a projectile motion question. If you'd like to see more videos of me explaining physics, go over to Eedeos Education and have a look at the videos that I've done on the topics of the Queensland physics syllabus. It's interesting to look back and see what would happen if we did this same velocity on the Earth, the same initial velocity on the Earth, and you'd get the negative 13 divided negative 9.8. That's a factor of 6 there, so you would actually have 1/6 of 8, which is about 1.3 seconds on Earth. And the same thing over here. Instead of being 2 times negative 1.63, it'd be twice negative 9.8. So you'd be dividing by a bigger number, and you get a smaller answer, 8.6 meters up in the air. So it goes far lesser height with that same initial velocity on the Earth. Pretty flat trajectory though, isn't it? It's only really, when you look at the moon trajectory, only 50 compared to 1,200. So it's a pretty kind of flat arc, it's a flat parabola actually. So there's a comparison. What about this last one here? If you now multiply the twice this, so that 2.6 seconds by that there, you'll get about 200 meters as the range on the Earth. So you can see that that's that factor of 6. Acceleration is a sixth, and it leads to, on the moon, 6 seconds long, 6 times as much time in the air, goes 6 times higher, and it goes 6 times as far. So it does turn out to be that simple. Just by way of comparison, I'm just going to attempt a bit of a sketch here. Say on the moon, trajectory looks like this, and there's 1200. This is the astronaut hitting it, 0. So distance travelled, and in comparison, on the Earth it would be about this far, a sixth as far. Yeah, it might be a little bit short there, but I'm just going to say it's 200, and you can see that it's far bigger, just in comparison graphically, the strike on the moon. Okay, so that sort of covered the things that you need to know in the Queensland syllabus as far as solving projectile motion questions. I'm just going to go off the track a bit. This isn't something you need to know, but I just think it's really interesting. If you compare that sort of behaviour with what actually happens when you play golf on the Earth, and I'm not a golfer, but I still think this is interesting. So if I now say I'm on Earth, and this now say this is 200 to here, right? So we've kind of zoomed in, and we're looking at this golf shot on Earth, and that's 200, and that's a parabolic shot. This is assume no air resistance, which is a pretty crazy assumption actually. When something's going 75 meters per second, there's going to be significant air resistance. So I've done a little research, and it turns out that because of air resistance, it actually only goes 120 metres. So, and it's not a symmetric path, so these are nice symmetric parabolas around a centre line. And on the moon you do get a nice symmetric parabola because there's no atmosphere. There's no resistance due to any gases here. This is just a vacuum of space travelling through. On the moon, on the Earth, you're not going to get that. It's going to start off pretty fast, and then it's going to be slowing down a lot, and you get this kind of tighter curve towards the end because the thing has slowed down so much. So this is the reality, 120 metres for what would happen on the Earth for this launch velocity, and with calculating in the air resistance. Now, this isn't actually what happens. This is the fascinating thing. Golf balls on the Earth with that sort of launch will actually go something more like 240. So now I'm going to get a different colour. So I'm going to go green. 240 metres is what a professional golfer would hit on the face of the Earth in spite of air resistance, and further than you can do with no sort of added effects. But the effect that you're adding as a professional golfer is that you're adding backspin. So there's an air effect which, if you spin the ball and you spin it backwards, you get what's an uplift force. It's called a Magnus force. The ball is actually pushing the air down, and the air is pushing the ball up. And so the initial part of the flight, actually, you can actually see the slight curve upwards as it goes up, like that, and then comes down. Apologies to the golfers, it's my shape, it's not the best, but the effect is it actually climbs up through the air before it comes down and lands. And then of course the all-important bouncing after it lands. If you're a golfer, you're really interested in to know what is added on with the bouncing afterwards. So that aerodynamic effect, uplift, the ball's in the air for longer, it's still going massive speed horizontally, and you can actually outdo the imaginary no air resistance parabola with golf ball on the Earth. So that's just a couple of little interesting things about golf trajectories. I have actually done this in class with students, talked about this path here, and the question usually comes up, so if you hit it that hard on the moon, doesn't it just go out into space? So you can look up what the escape velocity for the moon is, just Google it. Escape velocity for the moon is, where will I put that, escape velocity for the moon is 2.4 kilometers per second. You would have to hit it that fast to make it leave the moon and not come back. 2,400 meters per second, which is a lot more than the 75 that we began with. So you're a long way short of sending that ball into outer space. Just while we're talking about escape velocities, we'll just include the Earth. We'll see how fast you have to hit it. So we're talking there about 8 kilometers per second. So yeah, much faster on the Earth. So there we are. There's a look at solving problems to do with projectile motion and the steps that you go through. And then we've looked at some interesting facts around trajectories of golf balls, and that's golf on the moon.